that tells you how far a reaction proceeds, not how fast. So to be clear, right, the whole last chapter was about how fast. The next 4 or 5 chapters is just about how far. all the rate law stuff will disappear in this next section, except for the very beginning. They use rate laws, and we use the rate laws to talk about it. We're going to learn how to write and calculate K values. K's are equilibrium constants. And this is all worked out. This is just an overview. I left an L out here. Hang on. All right. Equilibrium constant is the measure of how far a reaction will go. Okay. The other thing we're going to do, and this is actually the hard part, we're going to learn how to use ice tables. The ice table thing that I showed you actually on the worksheet, I showed you how to do an ice table. The ice table thing is not hard to do. It's just very organized. So you just have to be organized. Every time you do one of these problems, you just got to write everything down. The hard part is solving the equations that come from the ice table. Okay? Get to that in a second. And the last thing we're going to do is sometimes you mix a bunch of chemicals together, or you don't get to choose the mixing of chemicals. Nature decides a mixture of chemicals. And you want to know, in this mixture of chemicals, like acid in your blood, or if you want to talk about base, which way is the reaction going to go in order to reestablish the equilibrium? Because what your body naturally tends to do is if I gave you something that makes you sick, what does your body have a natural tendency to do? Tries to fight it, right? Doesn't just succumb and go, well, that's it, I'm done, right? And so that's what we're going to talk about. We're going to talk about predicting reaction direction based on when a system gets challenged, okay? So let's get on from here. So imagine you got this reaction. The reaction is A goes to B, right? And so, well, that's beautiful. There you go. And I'm going to pop a bunch of animations up. I always forget to get rid of these animations. If we have a reaction and it goes to equilibrium, remember when you're doing mechanisms, what you would say is that if the system goes to equilibrium, you have a forward rate of reaction and you have a reverse rate of reaction. The forward rate is just K of the forward rate times this concentration. So we're thinking K forward. And all the stuff that you've seen up till now, that was always K1, but it doesn't really matter what the subscript is. Okay? And this one is K back. And in the stuff that I did in class is K minus 1. One of the homework problems was K2. Again, subscript doesn't matter. But it's KB times this concentration. Remember, this only happens if it goes to equilibrium. When you say that, you can say K forward times A is equal to K backwards times B. And in a rate law problem, you would solve for one of those and substitute. Okay? But you can also rearrange this and put all the constants on one side and all the variable things on the other side. In other words, you can take this expression, and I'll show you one step in between. You could write K forward over K back times A is equal to B, like that. And then you can just divide through by A, and then you get this expression here. So that's the in-between stuff that goes on there. Well, what is that telling us? It's telling us that at some point when the system comes to equilibrium, that ratio of A to B will always reach a constant. It'll always be a constant value. Now, what that constant is, we kind of put some terminology to it about whether or not there's going to be more products or there's going to be more reactants. But look at the way this thing's written, right? What's B? B is this reaction, reactant or product. It's the product, right? And A is the reactant for this reaction. So what this is showing us is that the equilibrium constant is based on a ratio of products and reactants. Now, it turns out, and I'll show this in another slide, if you had like two A's or two B's, those end up as exponents with the concentration, just like it does in the rate law stuff. Okay? So let's talk about a little bit about how big K is. Okay? So if K is equal to 1, what does that mean about products and reactants at equilibrium? Concentrations. What does it mean about their concentrations?
Equal in concentration.
Got to be equal, right? Yeah. Then A and B have to be equal. And we say that this reaction, if it's that way, is neither product or reactant favored. Now, K can be bigger than 1. There's like 3 possibilities, right? Equal to 1, bigger than 1, less than 1. Those are the 3 possibilities. So if K is bigger than 1, that means when a reaction gets to equilibrium, what do I have more of? Products. Will be product, right? Heavy, a lot of products. So B will be greater than A. And we say it's product favored. Okay, so just to give you the scope of products versus reactants, usually when they're within about, I don't know, when K is between like 0.1 and 10 somewhere, we don't really say it's product or reactant favored that much. But once you get to about 0.1 or 10, then we start saying like these terms, like I'm saying product favored. Okay. K can be as big as, like, I've seen K's in the 50s, 10 to the 50. Right? So think about what that means, right? 10 to the 50 times more product than you have reactant. Now, there's a limited amount of reactant, so basically what that means when the reaction takes place, there's no reactant left. Right? It all goes to products, heavily product favored. If K is really small, right, or K is less than 1, what does that mean about the ratio of B and A? Or the relative amounts of B and A? Which do I have more of? You have more reactant, right? So A will be more. So how I'm getting that makes sense, right? I'm just looking at the ratio and say, well, it's going to be less than 1, right? Then A has to be bigger than B to make it less than 1. So there's more A at equilibrium than there's B. What that means is basically the reaction doesn't make a lot of product, and we say it's reactant favored. So we have neither reactant nor product favored. We have product favored. We have reactant favored. Reactant favored, those K's can be tiny. I've seen like 10 to the minus 99. Right? Now think about what 10 to the minus 99 is, right? That's like 1 divided by 1 with the 99 zeros. It's super tiny. People do these calculations. And for fun, I did this one time. I found the smallest equilibrium constant I could find. I calculated what volume of water would I need to have 1 molecule dissolve. It's like the size of the ocean. Basically, it doesn't dissolve. But the other thing that freaked me out about it was somebody measured that. How do you measure that? Like, I don't even know. It's got to be super hard. Okay, and just to show you really quickly, all right, if the reaction is 2A goes to B, right, what am I going to write? Well, KF is equal to this. And then KB, right, will give me this. And let's say those are equal to each other, right? So I could say K forward times A squared. Oops, sorry. Let me do it like this. equals KB times B. And I rearrange that, and I'm going to solve for my constants. I'm going to say KF over KB, right, is equal to, that's a weird K, sorry, it hiccuped on me, is KF over KB times A squared equals concentration of B. And then I divide through by this, right? And then I get to this point here. Again, right? If I look at the forward rate over the reverse rate, I get a combination of products. This is product over reactant. So a lot of people say, well, why do you always calculate a product over reactants? Because that's the relative forward rate over the relative reverse rate. Okay. And even with a multi-step mechanism, you can work it out. If the system goes to equilibrium, this is what you do all the time. Okay. Okay. So in general, okay, right, at equilibrium, one thing to remember is the concentration are constant. That's the idea of equilibrium, right? I don't have very good balance, and in balance they refer to that as equilibrium, right? So we're all pretty good at standing straight up. But if you get pushed, what happens? You're out of equilibrium, and your body tries to readjust so you can get on to equilibrium again. Right? I realize this. How many of you have been on a stand-up paddleboard? You know what a stand-up paddleboard is? One of those boards you stand on top of in the water, and you never done one of those? See, I thought I was okay at equilibrium. Then we went to Lake Tahoe, and it was really wavy. For a kid, I had a son played a basketball tournament there. I stood up on the paddleboard, just straight off. I don't have very good. My kids, they're standing up there the whole time, but they're doing this. They have really good equilibrium. They're always reestablishing their center. Me, center goes out, I'm done. Okay. So here's the thing, right? Concentration and equilibrium are constant, but that doesn't mean within the system things aren't moving around. They're just moving in such a way that balance is always maintained. So like me, I can't do it, but like kids, their hips move still, their knees move, right? They're doing this thing, and it's Tahoe. I don't know if you've been on Lake Tahoe. It's going like this all the time. It's crazy. Motor boats going around, and they just stood up, and they were like, it was nothing. Anyways, it's not that they're standing still and nothing's changing. It's constantly changing, but they're always maintaining their equilibrium position. So that's something to think about dynamic equilibrium. Okay? Now, having said that, if the reaction looks like this is let me not do this. Like this is sort of really generic, super gigantic reaction, right? A is the stoichiometric coefficient, little a, lowercase a. I get corrected by my kids all the time. And uppercase a, lowercase b, uppercase b. The lower cases are the stoichiometric coefficients, the balancing numbers, right? You can write the equilibrium constant, it's going to look like this. So regardless of how many products you have or reactants you have, you can always end up with an equilibrium constant. All right. Questions? We're going to do some examples, let you guys practice a little bit. Okay. Before we move on, though, I want to talk a little bit about homogeneous versus heterogeneous. Okay. Homogeneous just means it's all in the same phase. So that means everything in the reaction is all gas or all aqueous, right? And then heterogeneous means you have solids and liquids mixed in with the gases or the aqueous, or you have gases and aqueous mixed together. So you have a bunch of different phases together. Okay? Now, one other thing about writing equilibrium constants for homogeneous reactions is everything is written into the equilibrium expression. So in homogeneous, all reactants and products are included. in heterogeneous reactions, okay, we leave out solids and liquids. And I'll explain that to you here in a second, okay? But in heterogeneous, right, solid and liquid concentrations are constant, and these are not included in the equilibrium constant expression. So when we write K equals, if it's a solid or a liquid, you leave it out. Let me make a little side note here. Okay, I'm going to make a little extra slide. Ooh, I'm going to use graph paper because that looks cool. So I want you guys to think about, this is not something you think about a lot, but I'm going to draw a cube. All right, so I draw a cube like this. And it's, let's say it's made of water. So what is an ice cube, right? Sorry. And I say that during the course of a reaction, the concentration of a solid or liquid doesn't change. So let's say water as ice, but it could be iron or any solid, okay? But just people have an easier time thinking about water as an ice cube. Gets used during a reaction. How would you calculate the concentration of the cube? Right, because molarity doesn't have to be just things in solution. It's just a number of moles per liter, right? So if you wanted to calculate the molarity of an ice cube, you would take the moles of ice and divide by the volume of the ice. So far, so good? That's what it is. Turns out it's like 55 molar. You don't think about these things, but it's kind of just a weird... And actually, like in organic chemistry, we actually use that number for calculations. But yeah, the molarity of water in water and ice are roughly around 55 molar. Well, ice is actually around 50 molar, but you know, it's about that range. Let's say I use half the ice, right? Half of it's gone. So take the cube, half of it gets used in the reaction. It's not that, you know, in a reaction, the top half isn't just going to disappear, but let's just pretend that, right? How did the moles of ice change? Right? If I use half the ice, I have half the number of moles, right? How would the volume change? It's half, right? How did the molarity change? No, because you're taking half divided by a half now, right? The halves cancel out. Molarity is the same. So solids and liquids get used in chemical reactions. Their concentrations are constant. Okay? And the only thing that we use in equilibrium constants for K values, Ks only reflect concentrations that change. And the rest is effectively part of the equilibrium constant because it's a constant number. And you can show that, like you work the numbers out and show that, but it's actually part of a way more advanced topic, and so we're going to leave that for now. Actually, we're going to leave it forever unless you ask me, and then I'll go over it. But, yeah. All right. So we're going to classify these reactions as homogeneous or heterogeneous, and then we're going to write the equilibrium constant expressions. And go ahead.
Can you just go back to the last slide? For
That one?
a second?
Yeah. So the next slide we're going to classify. Homogeneous, heterogeneous, and then we're going to write the expressions. Okay, those. When I say expression in science, it's not like the oh hey, it's not that expression. It's an equation. So I just say expressions. I just want to make sure you understand. It's kind of like jargon in a lot of ways, and I learned years ago that when you say stuff like that in a class, especially at like a community college, you got to say that's what an expression is, an equation. I one time said things fit together like nuts and bolts. You guys understand what that means? Right? Nuts and bolts, they screw together, right? An Iranian student comes to me after the class. He goes, what the heck does a nut have to do with a bolt? Because he was thinking like the nuts you eat. And I'm like, oh, that just totally didn't make sense to you. Huh? Yeah, anyways. He ended up going to medical school and becoming a doctor, so good guy. He's also a black belt, like multi-level black belt in, forget which it was, like Aikido or something. And just for fun, he said, oh, I can kick really high. So I said, well, how high can you kick? He kicked like the chalkboard, like over 6 feet tall. He kicks the top of the chalkboard with his foot. And he's like this tall. I'm like, oh, that was really impressive. You're getting an A. Actually, he did get an A, but beside the point. Is that?
Can I get an A?
Can you kick chalkboard? Yeah, and then you have to get like 90% and higher on everything. And then we'll give you the A. Okay. That's my idea of give. All right, so now we're going to calculate K. And I'm going to show you two things, okay? One is, well, what is that, homogeneous or heterogeneous? Top one. Homogeneous, because it's all in the gas phase, right? Bottom one is hetero, because this one's aqueous, 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 and that's a liquid. So when you write the equilibrium constant, you're going to leave the liquid out, okay? Let's do the top one first. You can either write these for concentration or for pressure. It doesn't really matter. But they're given different subscripts, and I don't want you to freak out about the subscript, okay? It doesn't mean anything other than I'm using concentration in my calculation. Molarities has to be molarity, not any other thing. Or I'm using atmospheres, okay? So those are the 2 units. So if I say Kc, what do you think I have to use? What's the C stand for? Concentration, right? So has to be in molarities. So we use those brackets for molarity. And what am I going to write? I'm going to write HI on the top. You can leave the states out. Squared. All right, divided by the concentration of H2 and the concentration of I2. Okay. If I say it's Kp, exact same expression, just use P's instead. So it's going to be P of HI squared divided by P of H2 times the P of I2. Now, if I2 had been a solid, which it often is, but it's not in this reaction, but if it had been a solid, you would have left it out too. It would have been heterogeneous. For this one, probably P makes more sense than molarity, but oftentimes in these problems, even if it's a gas, they just calculate it as the molarity because it's the moles per liter. And these 2 values aren't always the same, right? Equilibrium expressed in units of pressure is often different than equilibrium expressed in units of molarity. Sometimes exactly the same. We'll learn like what the situation is when that is. Turns out in this case they're exactly the same. Now this bottom one you can't write as a Kp because there's no such thing as a pressure of an ion in solution, and so these all have to be Kcs. So you would still write this bottom one as a Kc. And then before we write it, do this. A, B, C, and D. That way you don't have to write those things over and over and over again. So much easier to do that. Even when you get a problem in the homework and it says, oh, this is the reaction and these are the molarities, like assign A, B, C, and D to it and work it out. And when you do it, even like on tests, I'll know what you meant. If you start with A from the left and go through Z to the right, I'll know. Don't do that for other teachers. They'll get mad at you. Like, what's that? I'm like, who cares? Okay, so, sorry, I didn't mean to say it that way. So this is going to be the molarity of what? C, yeah. I would have been surprised if you told me the actual name. It's tetrachlorocobaltate 2. Yeah, anyways. Something like that. You learn that nomenclature at the end of the semester. And then what do I divide by? A, yeah. And B. Okay, am I done? What's missing? See this? Got to be to the fourth power. Yeah. So get ready. When you solve these equations, you got to know how to do that in your calculator. Okay, you're going to have to know how to do powers. Solve fourth order, fifth order equations. You have to know how to do that. It's not hard because you're going to use your thing called a solver on your calculator, and it does magic for you, right? For those higher order ones, there's a simple way, and I'll show you how to do it. We'll even do a worksheet on it. Other instructors say, oh, they can't do that because they have to learn how to use the quadratic. Well, learn that in a math class. Right? I'll show you how long it is to solve one of these with a quadratic, and then you're going to forget that happened, and we're going to use the solver. If you don't know if your calculator has a solver, ask me, okay? So anyways, equilibrium is expressed in molarity or pressure. So molarity are moles per liter, and atmospheres are for pressure. Just to be clear, though, and that we talked about this at the very beginning of the semester on that worksheet, you can relate pressure and molarity through the ideal gas law. If you remember, PV is equal to nRT, right? And you divide by V on both sides. I'll get P is equal to N over V times RT. Now, I just rearranged it a little bit, right? What's this? Moles per liter, right? It's the molarity of the gas. You take so if you know the molarity of the gas and you know the temperature, you can actually just calculate the pressure by multiplying by RT. Okay? You don't need to know the volume, you just need to know the molarity of the gas. So these two quantities, molarity and pressure, are related, and we're going to use that later to see how KPs and KCs relate to each other. Okay. All right, so you guys do these ones. And write them as KP and KC, because they can both be written as KP and KC. Give you like 30 seconds. If I had the Jeopardy music, I'd play it, but I don't have it. I'll write KPs, but the KCs will be the same, just with concentration brackets, okay? So you can fix it based on what I write if you get it wrong. Okay, top one. KP equals, what's on top? Pressure of PCl5, okay? All right. What goes on the bottom? Yeah. Yeah. And if you wrote KC, it'll look like this. I guess I'll write it. Okay. Like that. And then for the next one, this one always freaks people out. KP, right? equals what? PNH3 times PHCl. And then NH4Cl, the reactant, is a solid, so you don't include it. It's over 1 in essence. So you just write, that's all you write. So not all equilibrium constants look like their ratios of products to reactants, because some of the products or some of the reactants are solids and they just don't show up. Okay? The molarity expression would be the same as well. By the way, these ones are usually a lot easier to solve mathematically. Oops, sorry, Cl2, that's the other one. HCl. And when you look at the homework and stuff, I'll post that. They're going to have lots of problems just like this. In fact, there'll probably be some of the same reactions. We'll go back. Yeah, sorry. And I'm going to go over if you want to, the next slide is just more practice. If you want to do a couple, I'll just throw up the answers. Okay? But I'll probably just skip over most of that next slide. He has all the slides over here. Did you download them already, though? Good. Okay, and the next one, for these, there's two solids, right? So if you're going to do Kp for the top one, pressures. And then I'll let you do the Kc. On the bottom one, Kp would be equal to. Then there's all kinds of exponents. I'm just going to write the stuff down, and then you tell me what the exponents are here in a second. What's the top exponent for the N2? 2. And for H2O? 6. NH3? And for O2? 3. Right? You're all experts. Good. By the way, if you have any questions, like if you're not an expert, feel free to ask. I just say stuff kind of flippantly, and I'm trying not to just discourage people, but sometimes I just say stuff. So, okay. Put that back up. I keep switching slides really fast. Ooh, we're going to get our first set of problems. Want to see what solving a quadratic looks like again? It's on slide 25 on page 9. Nobody wants to do that. All right. Okay, so now what we're going to do is we're going to look at a nice table, right? Initial change equilibrium, that's what that stands for. Oh wait, did I skip a slide? I want to make sure I didn't skip a slide. Oh yeah, no, I'm going to go back up one. And it says, calculate the equilibrium constants from equilibrium concentrations. Okay, so this is the first kind of problem you should get aware of and learn. If it's already in equilibrium, you don't need a nice table. Okay. Now you can set one up, and then as you fill in information and it comes out that everything's on the equilibrium line, just go with it and calculate, okay? But this problem, like it says, at equilibrium, the concentration of N2O4 gas and NO2 are 1.4 millimolar and 17.2 millimolar, respectively, for the reaction shown. Calculate Kc. So, in general, like I tell people, organize your table, put your data in a table, okay? So I'll show you how you use it for this one. Just draw a line like this. I'm always going to leave space right underneath the equations on exams and stuff, so you can just write the table under the equation, okay? And then this is just the equilibrium value, so I just have to fill in the equilibrium values because it's at equilibrium. I got a little too sloppy. My table's bothering me. Okay, so I look for this. This is 1.4 for N2O4. So I'm going to write 1.4. And I know it has to be in molarity units, right? So the way you convert it to molarity, and I tell people this all the time, don't set up the unit conversions to go to molarity. Just write this, times 10 to the minus third molar. Just substitute for m whatever m is numerically. And that's converted to molarity units. You don't have to do anything else. Right? And then for NO2, it's going to be 17.2 times 10 to the minus 3 molar. And I know I could have shifted the decimal and stuff like that. It won't matter at the end. When you do the calculation, you're going to just type it in like it is there. Okay. So, part one is organize your data in a table. Part two is write your equilibrium expression. These could have been 1A and 1B because it doesn't matter what order you do that in. Okay. Double check your units. Right, I'm double checking my units as I go along. And then calculate. So K, C is what I'm looking for, is the concentration of NO2 divided by the concentration of N2O4. What am I missing? Squared. And then it's this is what's called plug and chug. You just put the numbers in and get your calculator out and just go like this. Okay. Now, if you can't do it on your calculator, then we can have a conversation about that and fix that. We do a worksheet on solving equations. And we can take care of it when we do that. And then you calculate. Somebody calculate that for me. I think it's 60 something, but I don't think I put it in the footnote of the slide. Actually calculate it in the next slide too. I was carrying too much junk around, so I pulled my calculator out. Probably not a smart move for a science teacher, but whatever. Oh, really?
Yeah, I
Oh,
don't know.
yeah, I guess it is less than 1, huh? It's going to 10 to the minus 6 divided by 10 to the minus 3 would be 10 to the minus 3. 17 squared, I have no idea what that is. It's like 200, 300, 300. Divided by, yeah. Okay. I'll buy that. What'd you get?
0.21. I don't know how many said things.
Well, the 1.40, right? I forgot the 0 here. So it should be 3.
So another one. 0.2.
Oh, yeah, that number does look familiar now. Okay, product, reactant, or neither? 0.211 means which is bigger, quote unquote, at equilibrium. Yeah, because the reactance is bigger, right, at equilibrium. Now, it's kind of tricky because there's a square in there. But here's the thing. Whenever we say product favored, reactant favored, we're only looking at K usually and not the reaction. So you have to be careful with that terminology because at equilibrium, it's not that way. It's actually, there's more product than there is reactant. So the product favored, reactant favored, we only apply to the number and don't look at the equation. Now, what's missing in my 0.211? This is bugging some of you like right now. Units. Perfect. Here's the deal. In equilibrium constants, we never write units. So when you leave the unit off on a test, like today if you leave the unit off, I'll say units -1. Sorry. Just so you know in advance. In equilibrium constant calculations, when you calculate an equilibrium constant, you don't give me units, I'm like, great. Perfect. There's a deep reason for that, but I'm not telling you because I don't have time to explain like the physical chemistry behind that number. But it is kind of cool. If you want to know later, I can explain it to you like why it's that. Okay. Example 2, right? The initial concentrations of N2O4 was 20 millimolar. Okay. And at equilibrium, it had a concentration of 4.52 millimolar. Calculate the equilibrium constant. So this is what we're going to do. I made my table. I know I'm not starting at equilibrium, so I need the whole thing. I need a whole ice table, right? Because I have initial concentration, and then it says at equilibrium something, right? So I need the whole table because of that. And I'm going to fill in all the information that I know in my table. And I got to write an expression for K as well. And then I have to solve the equation, okay? So we're going to go like this. What do I know?
The concentration of N2O4 was 20 millimolar.
And where does that go in the boxes?
The first box.
First box top left, yeah? So I'm going to write it like this because I want it to be in molarity units. And oftentimes I leave units out of a table and just write them at the end. And I just make sure everything I put in there has those units. So there might be a lot of conversions around my table. But whatever goes in here is now molarity units. Again, easy way to do it, 20 times 10 to the minus 30. What else do you know?
At equilibrium, it went to 4.52 millimolar.
Okay, you guys reading that right? At equilibrium, it's that. What box is that?
First one, last row.
Last row, bottom, right? Left, this guy here. That just doesn't seem like enough information to solve a problem. But I'll explain to you what we're doing and what assumptions are being made. Okay. If they don't mention a concentration, it's 0. Okay? If they don't tell you anything about it other than, like if they say solve for this concentration, then it's probably not 0. But if it doesn't say anything about the concentration, it's probably 0, which means this is 0 initially. Okay? Now, I explained this at the beginning of the semester, and I did that intentionally because it helps you understand better when I say it again. If I use, and just think about it without looking at the numbers on the table now. If I use 1 mole of N2O4, how many moles of NO2 would I make? 2. If I used a half a mole of N2O4, how many moles of NO2 would I make? 1. If I use 3 moles of N2O4, how much NO2? 6, right? It's always a multiple of the amount that it changes by. So this is what we're going to do. I know that the reactant concentration is going to go down, so I'm going to use a minus here. And I'm going to say it's going to go down by minus x. I'm going to put a 1 here, although we don't normally write the 1. The 1 represents the 1 that's up here. All right, so we're going to use this coefficient down here. Now the product is going to change by 2x, right? Because it's always twice because of the stoichiometry. It's 2 to 1, right? So you guys know the stoichiometry things, right? So I'm going to say this is 2x. And because the reactant is going down, the product's got to be going up, so I leave it as plus. Right? And I'm going to write the plus because I want you guys to see that it's positive, right? It's going up. So these signs indicate direction the reaction is going. It's the direction of the reaction. So all I know right now is if I take, this is my I, this is my C, and this is my E. If I take the I plus the C, it's going to be equal to my E. That's what I'm doing. Take my I and my C, make it equal to my E. I know, it's like your dad dancing, huh? It's like disgusting. It's cool. You'll remember. You can make a rap on that. It'd be kind of a weird one. I'm sure somebody's done it already. So all I know then is that this bottom line on the right-hand side is just going to be 0 plus 2x. All I need to do is figure out what x is going to be. And this is how you're going to do it. You're going to take the 20 times 10 to the minus third plus a minus 1x. So I'm going to just say minus x. I'm just adding these two together. That's equal to my 4.52 times 10 to the minus third. Tell me what x is. $15.48 times 10 to the minus third? Yeah? Good. Oh, there we go. Yeah. There. Bottom of the slide. And here you should use units of molarity because we're not doing a K yet. Okay. Now, to get the concentration, so that's the concentration, right? Change from the reactant from initial to equilibrium. And now what I can do is I can calculate, right, what I have at equilibrium for NO2 because now I have the value for X. So this is going to be equal to 30.96. Yeah, 39 times 10 to the minus third molar. So multiply by 2 and I get that. And those numbers you'd plug in for K. I got to make a reminder of myself, add some space to this slide. You got all that written down? I'm going to make a new slide right on top of the new slide. I'm going to just blank this one out, actually, go like this. So I know that K equals, now Kc equals the concentration. It's the same one as before. The concentration is NO2 squared over N2O4. And that's going to be 30.96 times 10 to the minus third squared divided by 15.48 times 10 to the minus third. And I think you get 0.211 when you do it again. Better double check. It's supposed to come out the same because it's the same reaction, and I just use the same reaction for two different problems.
So basically, you're just saying use a system of equations.
Yeah. But you got to know what equations give you the information you need to solve, right? And what I did was I figured out, oh, from here I have all the information to figure out X. Sometimes it's a product. You have all the information you need to figure out what X is. You solve for X, and then you do all the calculations. But again, data table, super handy for this. Okay, we'll do one more example problem. It says a mixture of 0.1 molar NO, 0.05 molar H2, and 0.10 molar H2O is placed in a 1 liter reaction vessel. And there's the reaction. And it's a homogeneous one, so you can include everything. All right. When the reaction reaches equilibrium, blah, 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 NO is 0.062 molar. Calculate the equilibrium concentrations of H2, N2, and H2O. Okay, so a bunch of things you have to calculate. And this will happen in lots of these ice table problems. You'll be asked to solve for a whole bunch of concentrations, okay? Especially in homework. Which remind me, I got to post that. So I was bad. I didn't write my table right underneath because I'm still rewriting my slides. I make a table like this. And I put NO at the top plus 2H2. My reaction arrow, equilibrium. I have N2 and I have 2H2O. And then I'm going to make 3 lines underneath like this. All right, so the one right underneath and then 2 more. This is my initial and this is my change and this is my equilibrium. And then I usually put lines to separate, look like this. Sometimes it's helpful to, under the equilibrium arrow, write which way the reaction's going so you can be sure that you have your pluses and minuses correct. So I leave a little space there. You don't necessarily need to do it in this reaction. So it's a 1 liter vessel. This one's 0.1. The H2 is that many moles in a liter, so it's 0.050. And the N2 is, no, H2O is 0.10 molar. Okay. I believe I meant to originally change that all into molarity units so we didn't have to think about volume, but that's all right. And then it says, when the reaction reaches equilibrium, the concentration of NO is 0.062. Okay. Which way is the reaction going? Left or right? How do you know?
Water concentration is going down, so it must be dissolving something.
Yeah, so, but if you look at the NO, right, it starts as 0.1 and it goes to 0.062. So it's going down, right? That's what that's telling me. It has to be going to the right. Even though there's other concentrations put up there, you have data for one that says it has to be going to the right. Which means this arrow that's going to be here, it's going to be pointing in that direction. And this is an important concept to think about. If this one's going down, right, then the other reactant has to go down too. Everything on this side of that arrow has to have the same sign. Everything on this side of the arrow has to have the same sign. Now, if it's going down, what's the sign that we use? Negative. So we pop a negative in here. Right? So you guys fill out the rest of that table, and you tell me what you get. Or tell me if it agrees with what I get. could have sworn I put all the answers in the bottom corners of each of these pages. I used to have them. But I seem to have unwittingly deleted all of those things in my edits. Poop. Go add them back in. Just get to the point where you fill the table out, and then we'll do the calculations together. But I want to check to see like you're filling it out okay. Okay? And even if you're not sure, just guess. It's fine. We'll fix it. All right, you guys want me to start writing? Yeah? Want me to write? I'll write. So the middle line looks like that. Right? Right. Minuses are all on the left side. Right? For a change of x, it'll be 2 x's for the NO. It'll be 2 equal to the change in H2, 2 x's as well. The N2 is on the other side, so it's got to have a positive, and so does the H2O. It has to have a positive. The only thing is just one or two things missing here, right? Depending on how you're looking at it. The one thing that's really missing is what's the initial concentration of NO? 0. Not given, you got to make that assumption. I actually don't like that about these problems, but everybody in the universe just assumes you know it's 0. They don't tell you, just say, well, you know it's 0. Well, I don't know how I know it's 0. I'm one of those people that says, well, I don't know that it's 0. And then the other part that's missing really is you just have to add these things up. So this is 0.050 minus 2x. This is x, and this is 0.10 plus 2x. The first column is how I'm going to figure out what x is. Remember, you take your I plus your c. Sorry. I do like that, though. I'd like to start to dig on that thing. Maybe next time I'll do the Super Bowl halftime. There's all some kind of controversy about it. I didn't even get it. I only watched like half the Super Bowl. You could see the writing on the wall. That's what you write. And you're going to solve that for a value of x. Okay? I kind of know that's the column in retrospect, looking at what I've written, right? All these other expressions all have x in them, right? This is the only one down here I don't have an x for. It's in the equation, but I can solve for it. I know what the concentration is in equilibrium. Okay, so solve it. What's x equal to? 0.0623819. So I get 0.019 molarity for x. So my concentration for H2 is going to be equal to 0.050 minus 2 times, right, 0.019. That's going to be 0.012. You could check my math because I'm just kind of eyeballing it. The concentration of N2 will just be the value of x is 0 plus x, right? And the concentration of H2O would be 0.062 molar, like that. Oh no, that's not right. I did backwards. I did something wrong. Let me erase that last one. It's embarrassing. Zero 0.138. I was like subtracting or something. I don't know what I was doing. I looked at the answer and go, that can't be right. It went up. All right.
So what you get for x, the x equals 0.019, you plug in that x too.
Yeah.
And then you solve? Okay.
Yeah, so I got this value here, right? And I said, oh, this is 0.050 minus 2x, so 0.050 minus 2x is equal to that number, if I did my math right, right? And then this one is just equal to x, so, right, it's just 0.019 for this one. And this one's 0.1 plus 2x, and in my head, the reason I screwed it the first time, I was trying to subtract it for some reason. So those are all my equilibrium concentrations, and now I can calculate the value for K, so I could say K equals something. Okay? Anybody do that already? So that's where we're going to stop today. I'll let you guys solve for K. K equals, I don't know what it equals. It's in my notes from my slides somewhere. Any questions? That's one of the last things to do, right? It'll be the concentration of N2 times concentration of H2 squared, H2O squared divided by concentration NO squared times the concentration of H2 squared, like that. Just had to jam it all in the corner. All right. And then you just plug those numbers and you'll get an answer. All right. I'm sure there'll be lots of questions later. Like right now, I know your brains are kind of full. I totally get that. So I'm going to go over and open up the lab, like now, and then we'll do a little reviewing there, or if you want to just walk around and clear your head, I'm totally okay with that. But come back just before 1:45, and we'll head over to Life Science C, okay?